Okay, good morning. It's my pleasure to introduce today's speaker, Dr. Naga Bhushan, the Vice President of Technology from Qualcomm R&D. Bhushan got his PhD from Cornell in '94. After that, he has been in Qualcomm, and he has been making a lot of contribution, especially for the standard part, for 3GPP standard, and he has more than 100 patents. So today he's going to talk with us about what's going to be after the 3G, 4G, what's going to be that. Okay, so let's welcome Bhushan.
Thank you very much. It's my pleasure to address this audience. So in today's talk, I will first give you a brief overview of Qualcomm and its many R&D programs in progress. Then I will give you a flavor of the 4G technologies, their evolution, and what we might expect in the next generation of wireless systems. And in the third part of my talk, I will go into the details of one specific set of ideas that we believe will play an important role in wireless evolution over the coming years. So let's begin with Qualcomm R&D overview. So Qualcomm, as many of you know, is a world leader in next generation mobile technologies. We have been around for about 25 years, developing key technologies for 3G and 4G domains of wireless communications. We are the world's largest fabless semiconductor company, #1 in wireless, a very recognized company, a global company. So our role in the wireless industry is somewhat interesting. We inject the wireless ecosystem with innovative solutions in terms of air interface technologies as well as mobile computing platforms that enable services on these technologies. So the wireless ecosystem that consists of phone makers, infrastructure vendors, service providers, operating system and application developers, they use the solutions we provide to create useful products that will then reach the subscribers, generating in a revenue stream that feeds the wireless ecosystem and then indirectly our company, the research enterprise and our company as well. So as you know, Qualcomm is a world leader in the smartphone arena. We have our chips in many of the dominant products in the industry, not just phones, but also tablets and other wireless devices that are coming into enjoying wide popularity in the recent years. So our focus is on integrating a large amount of diverse functionality into the mobile chip. It's not only the modem, but also the application processor, multimedia hardware, graphics hardware, GPS, and all the array of sensors that are making their way into the cell phones and other wireless devices these days. So the objective is to take mobile internet to the next level by providing always-on connectivity, enhanced battery life, instant connectivity, location awareness, multimedia performance with unprecedented power and speed. Mobile devices, or phones in particular, can be used as a remote control for your life. It can be aware of your surroundings, it may be aware of your habits, and it has easy access to the cloud with the copious amounts of intelligence that resides there. So the phone could combine all of these to become the most useful device that we carry around with us in the days to come. Now we'll zoom into the specific R&D programs that are in progress in Qualcomm. These programs may be classified into 4 broad categories. So the first one is evolution of wireless WAN in terms of 3G, 4G, and upcoming 5G technologies, hopefully. And then the second aspect is to innovate beyond wide area networks so as to encompass local area networks, body area networks, and so on. And then the third aspect is to enable smart applications on wireless devices by and thereby enhancing wireless user experience to a much larger degree than with just a communication device. And then the last aspect is to provide breakthrough performance in terms of the amount of number crunching and other complex processing that your mobile chips can do. So the third aspect is to enable phones to work smarter, whereas the fourth aspect enables it to work harder. So the combination will provide real value to customers. So let's focus on the first broad category, namely taking wireless WAN to the next level. We are working on several radio access technologies, the evolution thereof. So there is the 1X system, that's the first 3G system to come into being, pioneered by Qualcomm and other companies in the 3GPP2 standards forum. We are involved in a number of upcoming enhancements to this technology that's been around for a long time, almost 10 years. And then WWAN is an offshoot of the 1X system that is optimized for data. And there also we are spending a large number of resources on several enhancements, such as a smart network, which is a combination of macro and pico base stations and intelligent load sharing among them, and also a number of device enhancements and connection management enhancements to allow a large number of devices to be connected at the same time, consuming very small amounts of system resources while they are idle. And then HSPA Plus is the most dominant 3G technology today. So we are investing in a number of enhancements there in terms of multi-carrier, uplink, interference cancellation, voice over high speed, and uplink transmit diversity, where mobiles with multiple antennas can make good use of antennas to provide spatial diversity and possibly beamforming gains as well. And then the 4G technology, the most dominant one today, is the LTE, and we are contributing to a number of enhancements as a part of LTE-Advanced. This includes the so-called HETnets or heterogeneous networks. This topic is also going to be the focus of my talk today. Then there is coordinated multi-point processing, where base stations cooperate with each other rather than functioning as independent, almost independent entities at the physical and MAC layer. So the coordination can be in terms of steering beams away from each other, or in terms of sharing data among multiple base stations, so that you could use a regard the ensemble of base stations as a distributed antenna system, which can form very focused beams to the desired user, while nulling out any interference that could be caused at other users who would be served at the same time or on the same resources as the desired user. So that's multi-point comp transmission. And then we are also working on advanced interference management. That's an integral part of enabling high performance heterogeneous networks, and carrier aggregation that allows you to consume large amounts of spectrum and non-contiguous spectrum to provide extremely large peak rates and capacity to the system. And then we are also working on TD-SCDMA, which has some traction in China. We are working on advanced receivers to enable higher capacity on these systems, optimized resource management, robust mobility, as well as multi-carrier enhancements. Many of these features are similar to or have an overlap with multiple technologies, so we are able to leverage what we develop for one technology to quickly bring it to the fore on other technologies. So that's and then we also have we are also investing quite a bit of resources on femto cells. These are cells that are deployed by users to enhance coverage and capacity in their homes. Then CSNMs, which are the cell site modems, and the femtos station modems. These are in addition to the mobile chips that we are a dominant player in. And then we are also incorporating Wi-Fi, 3G, smart mobility between Wi-Fi and 3G systems, and then broadcast and multicast services on LTE. So those enhancements relate primarily to the wireless wide area networks. Now we have several projects that target other aspects of wireless. PNET is a project that's focused on high performance, low power radio for PAN or body area networks, very short range communication systems. And then Wi-Fi advanced, we are contributing to the number of .11 based standards that are being worked on in IEEE. Specifically the 5 gigahertz system with improved spatial multiplexing and 6 gigahertz band for extremely high data rates between devices in a residential setting perhaps. And then we have a project called FlashLink, which is whose objective is to provide proximal awareness, to provide ability to figure out what other phones, what other users and services are available to a given phone in geographic proximity. And then perhaps you may want to, if there is an interest in communicating with a proximal device, you could communicate directly with the device rather than going through the base station infrastructure. So this is a peer-to-peer technology with emphasis on discovery of proximal entities as well as direct communication among them. Then InNav is a project that's focused on providing very accurate indoor positioning and mapping tools for indoor location-based applications. Then moving on to the third area of enabling smart applications, we have a project emphasizing augmented reality, wherein we use advanced computer vision capabilities to overlay virtual content with real content to provide an enhanced experience to the user. Our role in augmented reality is to provide ability in our mobile chips to efficiently perform processing required for computer vision and the overlaying of virtual with real content, so that these applications can function better, faster, with lower power consumption on our chips. Then we have a similar project called Look, wherein which is focused on multi-language text detection and recognition with a mobile phone and coupled with a camera. So the two main problems here is to figure out which part of an image actually contains text, and then feed the information to a text recognition software, so that the user can interpret what he is looking at. So this is particularly useful when you're in a foreign country with signs in a foreign language. You could just point your camera, it would figure out where the text is and tell you what the text means. And then there is Listen, which is a audio counterpart of Look. It uses audio information to figure out the context in which the mobile and the user is embedded in. Then another project called Bettergranularity aims at providing efficient video delivery using a mobile device over HTTP. So this has to do with providing good, robust video streaming experience on a mobile device, which has to work under very harsh and time fluctuating channel conditions. Then there's another project called Aware, whose focus is to figure out what situation a phone is in based on a number of sensors that it has access to, and also correlate it with user behavior over time and try to guess what the user wants when he is in a particular situation. And then the last aspect is breakthrough in device performance. We have three subcategories here. The first subcategory of advanced radio technologies is to enhance the RF capabilities of the modem subsystem. The second capability is to take advantage of multiple processing cores that are available on the CPU to provide APIs that are highly parallelizable in the hardware, so that application developers can take advantage of the interface to write programs that will run very fast on these multi-core chips. Then Gryphon is another project whose aim is to provide a virtual machine interface that abstracts the fact that the underlying hardware consists of several heterogeneous processing cores. So the user or the application developer doesn't have to worry about the details of the multiple processing pipelines in the hardware that are more heterogeneous. They have different power performance trade-offs. So the virtual machine actually does the required analysis to partition the tasks among the different processing pipelines, and it also does so in a real-time fashion. It compiles the code, sees how it runs, monitors the performance, and then recompiles it during runtime, so that tasks are partitioned in a more optimal way to enable the device to operate in a more preferable power performance trade-off point. So now some of these slides go into further details of the different projects. So Peanut, I'm not going to spend too much time here. I'm just going to recapitulate what I mentioned earlier. Peanut is a project that's focused on short-range communication on a personal area or body area networks with low power consumption requirements, and it also provides very precise ranging. That's an offshoot of the project of the design efforts, and it provides a transparent audio codec for Bluetooth-like application with Bluetooth-like headphones playing audio music content. It also provides security with multiple inserted at multiple protocol layers, and range-based authentication, which is hard to overcome by an adversary who is not physically present at that location. Then Wi-Fi Advanced, we are contributing to .11ad, which is the 60 gigahertz band for very high rate communication among consumer devices. And then the 5 gigahertz band standard, which is the .11ac, which increases the spatial multiplexing order that the AP and stations are capable of. So it allows the AP with multiple antennas to serve different users at the same time, taking advantage of their distributed channel spatial characteristics, because the devices are in different locations. Then FlashLink is the peer-to-peer project wherein user devices automatically discover what services are available in the vicinity, and then also provides the ability to communicate directly with those devices in proximity, with seamless mobility between direct communication and communication through the infrastructure. So if two devices that are close together move out of range, the application can continue seamlessly, just that the physical layer, the data transfer is routed through the base station infrastructure. So InNav is a enabler for indoor location-based services. Consists of very high accuracy position location for the user device in a building, taking advantage of Wi-Fi access points in the neighborhood. It also has a crowdsourcing feature wherein information gathered from mobile devices by the map server can be used to refine the information that is stored in the map server. So when a new device enters the building, it can be provided with better data that enables the new device to compute its position more accurately based on the Wi-Fi signals observed by the device coupled with the parameters supplied by the map server. Then among the application enablers, smart application enablers, we have mobile augmented reality, combining the physical and digital worlds through advanced application of computer vision, machine learning, and mobile processing. Look, which enables you to detect and interpret text just by pointing your camera at the object. And Listen, which uses the audio signals around you to figure out the context, underlying context, and enable application developers to make use of this context to enhance user experience. And Wetterhorn is a project on efficient mobile video delivery via HTTP on mobile devices using advanced congestion control, rate selection, Raptor Q coarse for error concealment. And then there is a companion effort to standardize the required mechanisms, so-called DASH standard, that's going in progress in MPEG and other forums. So Aware is a project where you use sensors and user behavior monitoring to figure out the context again, and help the user based on that information, based on smart interpretation of that information by the phone. Then moving on to processors, we have advanced radio technologies focused on modem hardware with RF hardware, in particular with low power consumption, advanced transceiver capabilities, being able to tune to over wide range of bandwidths, configurable antenna and front-end filters. And then at the application domain, we have the Manticore project aimed at optimizing mobile computing or HTTP-like applications for a hardware platform with multiple cores, processing cores. And then Gryphon, which provides a virtual machine interface to the heterogeneous processing pipelines underneath. So in a mobile chip today, we have multiple processors and processors with different capabilities, different strengths and characteristics. They have the CPU, they have the DSP, we have the graphics processor. They all have different capabilities. So the virtual machine's task is to take a given application program and to partition the task optimally among these heterogeneous processors. Okay, so that completes the overview of our research projects. Now I'll talk about LTE and 4G in particular. So this would be the second part of my talk. So let's take stock of LTE and other 4G systems as they stand today. So I'll take LTE release 8 or 9 as an example of the current 4G system. So these systems can utilize up to 20 megahertz of channel bandwidth on licensed spectrum. So the carrier frequency that's used is mostly in the 0.5 gigahertz to 3 gigahertz range. And the technology supports both FDD or paired spectrum, where uplink and downlink spectrum are separately allocated, or it can function in a TDD or time division duplex fashion when you have just one single chunk of spectrum. So these technologies provide an average spectral efficiency of around 1.5 to 2.5 megabits per second per hertz per cell on the downlink, and between 1 and 2 megabits per second 1 or 2 bits per second per hertz per cell on the uplink. So the way to interpret this is that if you have a 10 megahertz system on the downlink, you can expect between 15 to 25 megabits per second per cell or per sector. And on the uplink, you can expect 10 to 20 megabits per second for all the users served by a given cell. And the primary FiMAC characteristics of these technologies, LTE in particular, is that it uses OFDM waveform on the downlink because it provides the best multipath mitigation, and it's also highly scalable with respect to bandwidth. So it overcomes one of the key limitations of 3G technologies in that they become cost ineffective as you go beyond 10 megahertz. So OFDM approach scales easily to tens and hundreds of megahertz in a cost efficient manner. So on the downlink, we use OFDM, but on the uplink, we use single carrier FDM because it has better peak to average characteristics, which allows for cheaper power amplifiers to deliver a given amount of power. And the other reason for using SCFDM as opposed to CDMA or other single carrier technologies is that SCFDM retains inter-user orthogonality within a cell, just like OFDM. So that's the rationale for the choice of waveform on the uplink and downlink. And these 4G technologies also provides ample support for single user and multi-user MIMO, wherein multiple antennas at the base station and receivers and mobile stations can be optimally utilized to provide diversity, spatial multiplexing, the key benefits of spatial processing. And then these technologies also incorporate good, they have the mechanisms built in for good QoS support with user or flow based prioritization by the base station. These technologies also provide mobility through network controlled association between mobile and base stations that can be seamless as mobile moves from coverage of one base station to another. So at the upper layers, the main features of LTE technology is that it's the core network has a decentralized flat architecture, which leads to very low latency induced by the core network, as well as better fault tolerance. There is no single point of failure. It's unlike a 3G network architecture. It's not hierarchical. It's completely flat and decentralized. So because the fault tolerance requirements are much less stringent, it allows infrastructure to be manufactured at reduced cost. So those are the main aspects at the 5 MAC and upper layers of the current 4G technologies. Now looking a little bit forward into the upcoming enhancements, these are almost standardized and being standardized and are expected to be deployed over the next 3 to 4 years by the operators. So LTE-Advanced incorporates several areas of enhancement. So we can classify those areas into a vertical enhancement category and a horizontal enhancement category. So the first among the vertical is doing more of the same things that distinguished LTE from the prior 3G systems. We can take it a step further, incorporate those features to a higher degree. So among them, the one that stands out mainly is carrier aggregation, that allows you to utilize up to 100 megahertz of channel bandwidth and even spectrum that may not be contiguous. So you could have aggregation of spectrum on multiple bands. So you could have one chunk of spectrum in 800 megahertz, another in the 2 gigahertz or 2.5 gigahertz, and the system can combine data throughput from both of those spectral chunks at the link layer without the higher layers having to be aware of it. And then we have support for improved MIMO on the downlink. The earlier releases of LTE goes up to 4th order spatial multiplexing. LTE-Advanced supports up to 8th order with 8 transmit and receive antennas on the downlink, and it also supports 2 transmit antennas on the uplink for transmit diversity and spatial multiplexing. And on the other kind of evolution is what I call horizontal. So these are features that didn't exist in the earlier release of LTE. So these encompass some new ways of looking at the problem and trying to provide useful features embedded in the LTE framework. So one of the main aspects of horizontal evolution is the so-called heterogeneous networks. So this consists of efficient support for macro-cellular networks that are augmented with small cells or low power cells such as pico cells, femto cells, or relay nodes operating on the same channel as the macro network. So in order to make such a system function optimally or sufficiently efficiently, we need advanced cell association and interference management well beyond the mechanisms provided in release 8 and 9. So as a result, releases 10, 11 of LTE incorporate support for aggressive load balancing through a technique known as range expansion of low power cells. It involves a clever interplay between interference coordination among cells, interference cancellation by the user equipment, and TDM or FDM resource partitioning by the collection of base stations. With the relays, it also incorporates a new data transfer topology. That is, instead of going just one hop on the air between the user and the base station, we allow 2 hops, a user to a relay node, which hops again over another wireless channel onto a base station or the core network that terminates the over-the-air connection. And then the second aspect of horizontal evolution is to take advantage of multiple antennas, either co-located at a given base station or distributed among multiple base stations. So this is together referred to as COMP, coordinated multipoint. So the one aspect of COMP is to use antenna or beam level coordination, wherein different base stations form beams that don't overlap with each other. So they should all have knowledge of which users each base station is serving, so that a given base station can point its beam away from other users being served by the neighboring base stations. So that's the antenna or beam level coordination. And then a more sophisticated level of coordination is to have data for a given user being made available to multiple base stations that are in its vicinity, so that the antennas of all the base stations that have access to the data can form one highly focused beam at the given user. The emphasis being not so much on increasing the energy received at the given user, but at steering nulls at other users who would be impacted by the transmission of this signal. So you could have either beam level or code or data level coordination. Another small twist on such a cooperation is in a deployment where macro cells are augmented with remote radio heads with fiber connectivity between the macro base station and a set of remote radio heads it controls. So you could have very sophisticated dynamic coordination between the macro and the remote radio heads underneath it. So this can be treated as so the RR heads can basically be treated as extended antenna elements of the macro cell. So you have now a macro cell whose antennas are distributed throughout its coverage area pretty much, and because of fiber connectivity, scheduling can be done as though the entire system of macro cell and its RRH is one single entity. So those are some of the enhancements that are coming up for standardization and deployment over the next few years. So what happens next? What's beyond LTE Advanced? So the challenges we encounter looking 8 to 10 years into the future is that it's widely anticipated that demand for wireless data would increase 1,000-fold over the next decade. On the other hand, it's accompanied by only a modest growth in projected revenues for providing this level of service. So what this means is that we need to reduce the cost per bit enormously to be able to deliver this outsized demand with only a moderate amount of revenue. So the nature of this demand comes in two categories. One is through a large density of connected devices, each device consuming only a moderate amount of throughput, and then there would be another class of devices, not so numerous, but each device would demand very high throughput. So these would be high-end tablets and even smartphones that gobble up large amounts of data. So we'll see them in larger numbers than we see today, but not orders of magnitude larger perhaps. But then there are going to be small devices, smart meters and other devices that are sprinkled all over the world pretty much that need to communicate with a server, but these devices demand very small amounts of bandwidth, small amounts of throughput, and they are active only with very low duty cycle, but there are going to be a very large number of them. So the system needs to support a very large number of terminals camping in dormant mode at the network. So these devices will need to consume very small amounts of resources while they are just camping, not really using the channel. But when they need to deliver data, the network should be accessible to it. And also these devices need to be extremely power efficient to be practical. So those are the challenges we need to overcome, and we need to do so such that the industry can be profitable while delivering much larger throughput than they do today without a corresponding increase in revenue expectations. So that's again emphasis on extremely low cost per bit for the network and very good battery consumption properties for devices. So we can brainstorm or we can speculate on what potential solutions might be to address this problem. Some of the solutions that come to mind I have listed here. So the first one among those is a super dense deployment of tiny cells. So this is a system where tiny base stations that are much cheaper and more numerous than phones are virally deployed by operators and users, perhaps hundreds of these tiny base stations in the coverage of today's macro cells. So these and in this environment, a user device needs to select the best cell among a number of tiny cells that may be in close proximity to the user device, but there's going to be some intelligence involved in figuring out which of these candidate base stations it picks. Not all base stations are meant to be serving users all the time. They're just there to serve the user who is most well positioned to be served by that base station. So a given user needs to pick among a set of candidate tiny cells, which is the best point for its for the first leg of its data transfer. So that's one of the interesting problems that come out. And we also need a low overhead discovery mechanism for these tiny base stations, or else with existing pilot structures, deploying such a large number of base stations would cause what we call as pilot pollution. You see too many signals which interfere with each other, so in effect you won't be able to use any of the base stations. So that problem needs to be overcome by replacing the current discovery mechanisms with much lower overhead discovery. You also need smart interference management among cells so that they don't jam each other and defeat the very purpose of their deployment. And the base stations in this environment can no longer be treated as trusted tamper-proof network elements, so new problems and challenges in security need to be addressed. So that's one solution. Another solution is to harness high frequency spectrum beyond 3 gigahertz, maybe up to 300 gigahertz. Some people are even talking about terahertz band communication. So, but in these frequencies, we need to overcome limitations of P8 power amplifier technology with respect to maximum power that can be radiated at these frequencies in an efficient manner, energy efficient manner. We also need with severe propagation loss that's accompanied that the signals face at these high frequencies due to rain and atmospheric absorption. So one way out, or some of the mechanisms that may help us out may be very high order MIMO, deploying very large number of antennas on these devices, which can now be very closely spaced because of the high frequencies. So these antenna arrays may to some extent overcome range limitations imposed by path loss impairments. We may also consider using wireless network coding for interference neutralization. That's an area that's been active in research for quite a while, and we need to see if it finds a niche in 5G going forward when we have much higher requirements for bandwidth and also applications that are multicast oriented. So network coding may be an important component of the next generation technology. And then we may also have to license venture into unlicensed or shared license spectrum paradigms such as TV white space in the US, authorized shared access spectrum in Europe. So in this regime, inter-operator and inter-technology coexistence becomes a issue of great importance. One of the caveats with this unlicensed or shared license spectrum is that unless there is a large amount of spectrum available, there will not be technology drivers, effective technology drivers that solve the problems that need to be addressed in this regime. So so this area also depends on regulatory policies that FCC and other similar bodies in the world adopt. If large amounts of spectrum is available, then we can anticipate some technological solutions to address the problems that need to be dealt with, or else if there is only a small amount of spectrum, it may not be worth the technological investment to fully utilize this kinds of spectrum. So those are some of the initial thoughts on how we might deal with the 1000x increase in demand over the next few years. So that completes the second part of my talk. Now let's get to the details of one particular type of enhancement that we envision is going to be important over the next 4 to 5 years of wireless evolution. Wireless networks of the future, in our opinion at least, consists of a few macro base stations with high transmit power and large coverage being augmented with lower power base stations such as Pico base stations or home base stations called femtos or relay base stations. So that's the preferred solution, we think, for improving the capacity of an existing network. So a operator would typically deploy a network initially for coverage, deploying macro stations at suitable locations, and as capacity demand grows, the most cost effective way to address that demand is not to deploy additional macro base stations. That's a very expensive solution. Instead, they would want to deploy lower power base stations in larger numbers so as to offload traffic from the macro base stations to these low-cost infrastructure. But this approach, although it seems attractive, it induces a number of RF challenges that need to be overcome first before such a deployment can give you meaningful gains. So an efficient network deployment needs to sustain a given demand profile with minimal network cost, but unfortunately the demand profile varies quite a bit over geography and time. So you cannot deploy, it's unwise to deploy macro based cells in general based on peak demand at one place, which could be quite, you cannot deploy a base station with uniform density because demand in different places could be quite different, and also at the same location demand over time could vary quite a bit. So you will not be able to deploy a homogeneous network that is adequate to address the peak demand at a given location or at all times. So a more prudent approach would be to deploy lower cost base stations. If the base stations don't serve anybody at some points in time, it's still okay. The cost is not so high as to make that economically infeasible. So you deploy base stations so that they serve users when there is demand, and at other times, even if the base stations are idle, it does not cost you so much as to make such a deployment untenable. So that leads to a solution of heterogeneous networks, where you deploy macro base stations at one tier and augment it with low power infrastructure, low power, low cost infrastructure that can serve users and that can pick up demand in a dynamic fashion. And because demand can be varying over time and space, any kind of cooperation between these different base station infrastructure nodes would also have to be dynamic. Depending on the traffic demand, you may allocate more or less resources to these smaller base stations and take away resources when they are not needed at one location or one set of base stations, transfer the resources to another part of the infrastructure where they are needed. So that's a new paradigm that cellular deployments will have to come to grips with. So before we go further, let's establish some terminology. So macro base stations refer to regular E-node Bs, enhanced node Bs as they call in 3GPP. So these are regular base stations that use dedicated backhaul and is open to public access. Their transmit power can range in the neighborhood of tens of watts. Then Pico base stations refer to low power base stations that use dedicated backhaul connections like the macro base stations and provides open access to all users, and their transmit powers range in the hundreds of milliwatts to a few watts. Then home E-node Bs are consumer deployable base stations that utilize consumers' broadband connection as their backhaul. So the home E-node Bs may have closed subscriber groups in the sense that they provide access to only a set of designated user terminals. So if another foreign user terminal ventures close to this base station, although this base station provides the strongest signal to the user, that it cannot be used to serve the given user. It only acts as a source of interference to the user when the femto base station is serving another user in its subscriber group. So that induces an interference challenge that needs to be addressed. And then finally, relay base stations are similar to Pico base station, except that their backhaul is also wireless, and typically they may use the same or similar radio access technology to go from the relay to the core network through typically another donor base station. So a heterogeneous network is defined as a deployment that supports a mix of these different types of base stations on the same spectrum. So let's look at the interference challenges introduced by adding Pico base stations to a macro network. So you have a macro that has number of Pico base stations in its footprint. So as you would expect in a cellular deployment, the users that are most disadvantaged are the ones that are located on the boundary between two cells. So most deployments are interference limited rather than range limited. So interference from base stations that are almost as strong as a serving base station is what limits the performance of most users. Now when you add Pico base stations, you have more cell edges than before, so more users would be disadvantaged. And so that's one challenge that needs to be overcome. The other challenge is that because the signal from the macro base station acts as interference to the Pico base station, the natural range of the Pico base station is highly constricted, highly compressed when it's deployed on the same frequency as a macro base station. So not only is the range of the Pico base station limited by its own transmit power, it's even more greatly limited by the higher transmit power of a macro base station that's deployed in the vicinity for coverage. So note that you cannot decrease the transmit power of the macro base station because that would cause coverage holes in those locations that are not inhabited by Pico base station. So you cannot reduce the power of the macro base station unconditionally, but we somehow need to protect the Pico base station from the excessive interference that's caused by the macro transmission. So in fact, in this scenario, network capacity can be improved if we could somehow have user terminals that see stronger signal from the macro to be served by the Pico base station instead. Because if the just intuitively, if the user terminal is closer to the Pico than to the macro, it should be served by the Pico even though it may see a stronger signal from the macro. So in other words, you want to increase the footprint of the Pico base station so that it serves a comparable number of users as any other base station in the network. So, but to do that, we'll need to address the RF issues created by the fact that macro signal acts as interference to these users who are outside the nominal coverage of Pico base stations, but who should rightfully be served by the Picos nevertheless. Now let's look at another RF challenge induced by a heterogeneous deployment. Here you have home eNode Bs that are deployed under the footprint of a macro. Because home eNode Bs typically typically have close subscriber groups associated with them, a subscriber who is not in that closed group, when he is close to a given base station, will suffer interference from the femto and go out of coverage from the macro, which is supposed to serve that user. So the presence of home eNode Bs, although it improves the performance for devices in the subscriber list of the home eNode B, will actually hurt the performance of other users who venture in its neighborhood, into its neighborhood. So that's an interference problem that needs to be addressed. Now with relays, we have a combination of these two problems that we saw with macros and Picos. On the one hand, relays have low power, so they need their range to be artificially expanded just so as to overcome the adverse impact of the macro signal. Otherwise, you would not have any meaningful offload of traffic from the macro to the relay. So that's one aspect. On the other hand, a node that is close to the relay may still want to connect to another node that is a user that is close to a relay may still want to be served by another node that's far away from the user, because the relay that's close to the user may have a poor backhaul. So association decision should also take the backhaul quality of relays into consideration. So this is a new paradigm that did not exist in any of the earlier deployment scenarios. So in some cases you may want to compress the range of a relay. In other cases you may want to expand the range, and which of the two needs to be done depends on the particular state of the relay, whether the relay is hurt more by its low transmit power or whether it's needs to be decommissioned in a sense because of its poor backhaul. So association between a user and a base station is no longer just a function of the signal quality, the default signal quality that's received from all the base stations, but should also take into account the loading on individual base stations, which could be very different between macro and low power nodes, and it should also take into account backhaul quality or other similar metrics that influence the overall throughput that the user will eventually see when he connects to a given node. So to address some of these problems, we develop new paradigms, and one such paradigm is the so-called idea of range expansion. So in a co-channel deployment, SINR coverage of low power Pico or relay base station is greatly reduced due to the presence of high power transmissions from a macro base station. So the diminished reach of Pico or relay base stations limits the amount of self-splitting you get as compared to a traditional self-splitting approach where you deploy more macro base stations in a deployment. So when you deploy Picos, the objective was to offload traffic from the macro to the Pico as much as possible. So load balancing between macro and Pico base stations is essential to harvest full benefit of these no power base stations. So range expansion allows users to be served by a Pico or relay base station even if the SINR associated with the Pico or relay is much lower than the SINR associated with the macro. If the relays or Picos happen to be much less loaded than the macro, we should somehow enable the user to connect to the low SNR Pico node instead of the high SNR macro node. So in order to enable such a unconventional association, we need these Pico base stations to transmit signals that have deep penetration. So even though the nominal SNR of the Pico may be low, there are some signals that can still be reliably detected by the user. We also need the control signals of the Pico base stations to have a much larger coverage than the nominal coverage for uncoordinated data transmission perhaps. We need smarter server selection algorithms based on path loss or distance or load more fundamentally, backhaul capacity and other metrics in addition to just the pure nominal SINR consideration, nominal SINR metric. And in order for data transfer between the Pico and the user terminal to be protected from the macro interference, we need interference coordination techniques which could be which should preferably be dynamic, so that when a Pico needs to serve a user, macro vacates certain resources, stops transmitting on certain time frequency resources, so that data transmission from the Pico will not suffer from interference caused by the macro on those particular resources at those times. So one way of enabling such resource partitioning is to take advantage of the HARQ interlacing, the hybrid ARQ process in LTE or similar systems that induce a certain interlacing structure. So in LTE, for instance, the separation between the first transmission of a signal and of a packet and the second transmission is about 8 milliseconds, and there is a regular 8 millisecond pattern that is created by the HARQ process. So we could allocate certain interlaces for the exclusive use of Pico base stations. So on these interlaces, macro base stations will either reduce or completely shut off their transmissions. So on these interlaces vacated by a macro, all the Pico base stations underneath the macro can serve their users without being impeded by the interference from the macro. So a single macro node giving up a certain amount of resources allows maybe 10 Pico nodes to use those resources. So you have a much higher spatial reuse as a result of this partitioning mechanism. So this is to be contrasted from traditional fractional frequency reuse in a homogeneous system, where one base station gives up resources and maybe another base station benefits from it. More likely, a large number of base stations in the vicinity need to give up a certain amount of resources so that one base station may use those resources more efficiently. So here fractional frequency reuse will cause a net a large loss in the average or median throughput of the system. So in such systems, fractional reuse is employed only if the cellage performance is so poor that you need to bring it up at the cost of average throughput. Whereas in the case of heterogeneous deployments, a macro base station gives up resources so as to improve the overall spatial reuse across the system. So it could be a net win both for the median throughput and tail throughput. We will see that shortly when we present a few simulation results. So the simulation scenario is where we have a hexagonal layout of macro base stations, and underneath each macro base station we embed Pico base stations. In this simulation they were placed randomly, and the users were also placed randomly throughout the network. Some of the details of the simulation framework are listed here. I won't spend much time here. So the performance resulting from such a system with various Pico densities and with or without range expansion, or with or without smart resource coordination, are shown here. So this curve shows the distribution of user throughput on a macro only system. And this curve shows the user throughput distribution when you have 10 picos underneath each macro, but there is no resource coordination between the pico and the macro layers. So here you see that there is hardly any improvement in the tail throughput or even the median throughput. It's only a few lucky users who benefit from the presence of the pico base station. So in this scenario, because there is no resource coordination, although you place 10 picos underneath each macro, a large number of pico base stations don't have any users to serve. So they are simply not providing any benefit to the system. And a small fraction of the pico base stations find a user that they could serve without any aid through resource coordination. And these users who happen to be served by the pico base station get very large throughput, but majority of the system sees absolutely no difference from the deployment of 10 pico base stations per macro. On the other hand, if you just deployed 2 picos per macro, but you allocated some interlacers, some resources to the pico base stations where you would not have to deal with macro interference because macro does not transmit any signal on those resources, then even with just 2 pico base stations per macro, you have a somewhat improved user throughput distribution. And with increasing pico density coupled with coordination, you get much more impressive gains at the median and tail throughput. So this emphasizes the importance of resource coordination and smart association and aggressive load balancing in a system with heterogeneous infrastructure deployment. So understanding of the capacity gains is that for every macro node that gives up a certain amount of resources, multiple pico nodes take advantage of it, thereby giving you a drastic improvement in the very attractive improvements and even in the median throughput, not just the tail throughput. And another note here is that in order to enable time domain coordination among base stations, you need the base station signals to be synchronized. LTE by default does not require base stations to be synchronized, but if you do synchronize networks, you can allocate certain subframes to one class of base stations, certain other subframes to another class of base stations, so you have these impressive gains that we saw in the previous set of results. Now, the arguments in favor of time synchronization is that it not only enables this kind of smart resource coordination in a heterogeneous deployment, it also enables many other features that are of interest to 4G technologies. For instance, it's mandatory for a TDD operation where uplink and downlink are not separated in frequency but in time. So here it's important that different base stations in a neighborhood employ the same uplink downlink partitioning as well as the same timing, so that you will not have uplink of one segment of a TDD system interfering with the downlink of another segment, another portion of the TDD signal. So because user equipment can be arbitrarily close to each other, the interference created by one UE's transmission, one user's transmission, when another user is trying to listen to a faraway base station, could be quite serious. So for TDD, time synchronization is inevitable. For single frequency network based broadcast multicast services such as EMBMS and LTE, you again need base stations to have very, very accurate synchronizations, so that all base stations, when they transmit a given signal, should appear as though they are multipath components of the same signal to the receiver. So this obviously requires fairly accurate synchronization. And synchronization is also needed for cooperative MIMO techniques or COMP techniques, wherein you use antennas at multiple base stations to deliver the same signal in a very carefully synthesized beam pattern. So that's another technology that would benefit from time synchronization. So in summary, time synchronization is not needed not only for this particular technique of managing resources between macro and pico, but for to enable many other interesting and useful features for LTE and similar systems. Okay, now we move on to relays. Relays, as you recall, are similar to pico base stations, except that they also rely upon a similar wireless access technology for its backhaul. And they create interference and association problems that are similar to those we saw in the context of Picos, but also similar to what we would encounter with femto base stations with close subscriber groups. So a user may associate with a relay even if he sees weak signal from the relay. On the other hand, he may not associate with the relay even if he sees a strong signal from the relay, but the relay has poor backhaul. So again, to enable such unconventional association configurations, we need sophisticated resource coordination between relays and higher power base stations. And the main advantage of relays over other types of base stations is that they are extremely cheap to deploy. They don't even require the operator to provide a dedicated backhaul. So they can be deployed almost anywhere, and with the expected reduction in cost of base stations, the backhaul cost becomes the main bottleneck in deploying small base stations in large numbers. So relays provide an attractive alternative to Pico base stations if they can somehow ensure a sufficient number of relays with reasonably good backhaul quality and sufficient density of such relays over the network. So with relays with a similar exercise of resource coordination and versus no resource coordination, we found attractive gains on the median and tail throughput of users. So we found that with 10 relays per macro cell, we saw about 50% increase in tail throughput and about 80% improvement in median throughput. So this again makes a case for heterogeneous deployments with the associated mechanisms of resource coordination and smart association between users and base stations. So just to summarize, enhanced UWEE association, which includes range expansion of low power E-node Bs and systems centric criteria for server selection, are key ingredients in ensuring good throughput improvement with heterogeneous networks. So adaptive resource partitioning for interference avoidance is necessary to sustain data traffic between a user terminal and a weak base station, wherein even though the base station signal is nominally weak, on those resources and at those times where the weak base station serves the user, the stronger sources of interference shut off their signal to ensure reasonable SNR for the reception of desired signals. So relays with range expansion and interference coordination also enables network capacity and coverage. So the conventional wisdom with relays is that they are mostly deployed for coverage. You put them on at the cell boundary so that they help disadvantaged users. But coupled with these advanced techniques, relays can also provide meaningful improvements in capacity. So even in a dense urban network, it makes sense to deploy relays, not necessarily in cell edges, but also in the interior of a cell. And coupled with the other techniques that go hand in hand with heterogeneous deployment, relays can also provide capacity improvements just like macros or femto base stations. And the proposed features of LTE-Advanced utilize, with these proposed features, a HetNet deployment in LTE could provide dramatic gains in capacity and coverage, which as we saw is indeed urgently called for as we move towards the next generation of wireless systems. So that concludes my talk, and I would be happy to take any questions.
Question?
Macro system, I have a question with, because the device obviously has to communicate back, so how does it work that the range of the macro system is so much greater than the Pico, the macro and the Pico? How is their range so much different when the device has to communicate with both, and the device is obviously the weaker communicator?
Okay, so the reason the the question is, how is it that there's a wide disparity between the range of macro and Pico base stations that does not impact the ability of the user terminal to communicate back to the macro? Because obviously the user terminal's transmit power is much lower than that of either the macro or the Pico. So the reason is that when a user transmits, there is adequate precaution taken by the infrastructure to ensure that there is no other interference. For one thing, when a user transmits, the base stations would all be silent, and it's the only source of interference for a user's transmission at the base station is the transmission of other users in neighboring cells. So the range is in all cases limited by interference. So it's tightly the range is tightly coupled to which other transmitters are active at the same time as a given device. So a device could reach the macro, but still a Pico would not reach the device because the Pico transmission is interfered by the macro. Any others? Yes.
So I noticed that there's a large disparity between your peak rate for spectral efficiency versus your average. Yeah. It's like a factor of 10.
Right.
So when you say all this heterogeneous networks, is that trying to improve your average rate, or is it just basically doing more cell splitting, giving you spatial reuse? So whereas your number of cells goes up, but your average bits per second per hertz per cell just stays the same.
Yeah. So the question is, what's the main objective of these heterogeneous deployments? Is it to improve the spectral efficiency, or just to there was one comment made about the large disparity between peak rates and average rates, and there was a question as to what the real objective of heterogeneous deployments is in terms of spectral efficiency versus throughput. Yes, peak rates are indeed much larger than the average rates. They are mostly a marketing gimmick to a large extent. You try to design into your system as high a peak rate as you could meaningfully do. The peak rates, however, can be achieved mostly in a lab setting or on a very lightly loaded environment. That is why I mostly emphasized average throughputs and more than average throughputs, median throughputs in this talk. In a homogeneous system, average and median there may not be too much of a difference between, but in a heterogeneous deployment, again, the average rate and median rates could be as far apart as an average throughput and peak rate in a homogeneous system. So in general, it makes sense to talk about tail throughputs definitely, and then median throughputs. So other metrics such as peak rates and the average rates can be misleading. And the objective of heterogeneous deployments is to increase the throughput per unit area. So all subscribers and service providers care in terms of demand is how much they can cater to per physical area. So although the spectral efficiency per cell has not changed dramatically, that's also unreasonable to hope for because we are already reasonably close to the channel limits and so on. So raw spectral efficiency will not change unless you increase degrees of freedom through MIMO, which can only go which we can only do to some extent. So the main thrust here is to increase throughput per area rather than throughput per cell, and heterogeneous networks provide a very powerful technique to accomplish that. So that's also a very good question. People are fixated on throughput per cell, but it only makes sense when all cells have similar footprint. In that case, it indirectly translates to throughput per area, but in a heterogeneous network, the fundamental figure of merit should be throughput per area rather than throughput per base station node. All right?
Any more questions?
Just following up on that, so are now people in academia now trying to look towards throughput per area, or is everyone's still very much fixated on just per cell?
They ought to be looking at these kinds of things. In fact, they should focus on throughput per area and median throughputs and throughput histogram more than average metrics. And they should also hopefully come up with a theoretically optimal framework for association algorithms and resource coordination algorithms. We have some ad hoc approaches we have tried, and they provide very interesting gains, but we don't know how close they are to the optimal. So with these talks, one of the objectives for me is to encourage academic community to look at this problem from a theoretical standpoint and establish the performance trade-offs in this paradigm.
All right, if no more questions, let's give Bhushan another big hand. Thank you.